Hey guys, welcome back. We are in Unit 3, Day 2. Whoop, whoop. Okay, so we're going to talk about what's called implicit differentiation. So just say it aloud, it's kind of fun. Implicit. And you're like, well, what the heck? What does that mean? So far, you have been doing explicit differentiation. Explicit has just been when we've already got a y equals or a function notation of something equals. So it's all in terms of the one variable and then it equals y, okay? Implicit is when you don't have it solved for one variable, like you don't have a y equals all in terms of x or, a y equals all in terms of t or something. Like this one up here would still be explicit. So you've got all of them together. Now, sometimes you can rewrite and get it into explicit, and yay, okay, we're happy. But a lot of times, like here, if I went and tried to solve for that y, I'm going to get two functions. Okay, we don't want that. And here, I mean, I challenge you to go try to solve for that y in this function. Okay, so this is not something that we can easily get into a y equals. So we're going to have to learn another rule. And I kind of break it down into the steps to help me out. And I just say differentiate all the sides with respect to x. Now, sometimes they may ask you to differentiate with respect to t as well, but these are usually the two things that you differentiate with respect to. So with respect to time, a lot of times, like change in position over a change in time. So you may differentiate with respect to time. Then you're going to go and you're going to take all the dy terms and put them on one side of the equation, and then everything else, go put them on the other side of the equation. And then factor out the dy dx, and then usually divide or something, and solve for that dy dx. That's the goal. My goal is to solve for dy dx, okay? So let's look at the first example. So I'm going to take, here, let me just rewrite it real quick. And I'm going to take the derivative of this. So this would be 1/3 x to the negative 2/3. But now we're going to say we took the derivative of x with respect to x. Plus, we're going to take this derivative. Do the power rule still. 1/3 y to the negative 2/3. But now we took the derivative of y with respect to x equals the derivative of 19 is 0. Dx over dx is just 1. So whenever we're differentiating x's, we don't really need to worry about the whole dx. It's when we're doing the variable that's different than what we're differentiating with respect to that we have to do that variable over dx. Okay, so now I'm going to keep everything with a dy on this side, and everything without a dy I'm going to take over to the other side. So this would be subtracted over. And now I'm going to solve for that dy dx. So I'm going to divide both sides by the 1/3 y to the negative 2/3. Then let's definitely adapt this. So 1/3 over 1/3, I just have that negative, and then move the negative exponents. There we go. So dy dx equals this right here. Okay. Do another one. Oh, I have it on the eraser, that's why. Okay. I'm going to rewrite this. So now we have to take this derivative. Guess what? This derivative is a product rule. And we can do separately with pluses, but now this derivative is a product rule. You almost always want to look for the product rule when you're doing implicit. It's gonna usually show up. All right, so this is the first times the derivative of the second, but we took the derivative of y with respect to x, plus the second times the derivative of the first, and there's just that first piece derivative. So now I'm going to say plus. I'm going to take the first times the derivative of the second, plus the second times the derivative of the first. But I took the derivative of y with respect to x. This piece is the derivative of that, equals the derivative of -2, which is 0. So this piece is the derivative of that. Okay, so now anything with a dy dx, we're going to go to this side, and anything without a dy dx, we're going to take over to that side. So then I subtract, and I subtract. Now I can factor out my dy dx, and I'm going to factor and divide all within one step. If that's too hard, then take the 2 steps. But I don't like to write tons of lines, so I try to put a couple steps together if I can. Right? There's your answer. Cool. Yeah. All right. So now this one doesn't want me to derive with respect to x. This wants me to derive with respect to t. So I'm going to take the derivative of y, and I took the derivative of y with respect to t now. Equals, I can think of these as separate because it's got a minus. So the derivative of 3x is 3, but I took the derivative of x with respect to t. So that's different. Before we were doing it with respect to x, so it went away. Now it doesn't. Minus 5. Coefficient along for the ride. Ooh, we've got a chain. Derivative of the outside. Leave the inside alone. Times the derivative of the inside. And I took the derivative of x with respect to time. So now it's telling me I want to go solve for solve for dx dt when dy dt is 3 and x is 2. So I'm going to go ahead and plug those in. And then I'll go solve. I'm going to put all that together. Put that pi at the beginning. And I'm just going to change the order and make that 2 pi. But wait, I know what sine of 2 pi is. 2 pi is over here. So what is sine of 2 pi? 0. All of that term goes away. So what is dx dt now? 3 divided by 3, which is 1. That was convenient. All right, so this wants me to find the derivative and evaluate at this point. So now instead of just plugging in x's like we did with tangent lines, we have to plug in an x and a y. So first go and solve for dy dx. Then go plug in your point. Okay, so this part over here is definitely a chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. But now I am differentiating with respect to x. So when I take the derivative of x, I don't need to say dx dx because we've already, that's just 1. Plus the derivative of y, but I do have to put dy dx. So there's the derivative of that piece. Equals 3x squared plus 3y squared dy dx. This was the derivative of that piece. And this was the derivative of that piece. Okay, so now I've got to solve for this dy dx. So let's see. I'm going to go ahead and distribute so I can get this term, kind of all the dy dx's by itself. So this guy times 1 plus this guy times 1 dy dx. So now everything with a dy dx is going to go to that side. Everything that doesn't have a dy dx is going to go to that side. And I'm going to factor as I move them out. So that when I bring it over would be a negative. And now I can divide. And I'm going to simplify my life a little bit by factoring out a 3, and it could go away. So I could take a 3 out and take a 3 out, and then 3 over 3 is 1. Okay, so there's my dy dx. Now I want to go find dy dx evaluated at the point -1, 1. So this would be 1 minus 0 over 0 minus 1, which gives me -1. All right. So I want you guys to go ahead and use this function and see if you can get that for dy dx. Go ahead and pause me and see how you do. And then unpause when you're ready. Good. So I've got that to work. So now it wants me to write an equation for the tangent line. Oops, typo, curve. Okay, at 1, 2. So I've already got a point here. I just need a slope. So I need to go find this dy dx evaluated at this point. So 6 times 1 squared is 6, minus 2 squared is 4, over 2 times 1 times 2 is 4. So 2 over 4 would give me 1/2. But I want the equation, so I have to do y minus y1 equals the slope times x minus x1. Okay, let's try this AP example. 2 examples left. These AP examples crack me up. A boiled potato. Okay, at time equals t equals 0, a boiled potato is taken from a pot on the stove. Oh, so I got this pot on a stove. I got my potatoes in here. Okay, need some steam. Okay, and so this boiled potato is taken out of the stove and it's left to cool. Let's go ahead and put it on a plate. Get these eyes on the potato. Okay. The internal temperature of the potato is 91 degrees Celsius when the time is 0. So boom, take it out. The very first thing it is 91 degrees. Okay. And the internal temperature of the potato is greater than this, and that's degrees Celsius even, than 27 degrees Celsius for all T greater than 0. So it always stays greater than that. That must be like room temperature. The internal temperature of the potato at the time in minutes can be modeled by this differential equation. So H of T is measured in degrees Celsius. And then they give me this initial H of 0 equals 91, which we already knew. When time was 0, I was at 91 degrees. Wants me to write an equation of the tangent line to the graph of H here when my time is 0. Then we're going to go approximate. But let's just try to get this first part. An equation of the tangent line. Oh gosh, that was bad. Equation of the tangent line. Oh, my pad is switched. That's why. Okay, at t equals 0. So I know I'm going to have to get my slope. So I want dh dt. When my t is 0, that means at this point, 0, 91. So this is kind of like at t and at h from what they have going on. So we're going to go plug that in to our equation. There are no t's to plug in. That's the tricky part of this one. So we're going to plug in only the h. And the most common mistake that kiddos make is they plug 0 in for h, and that's not right. So I get a slope of negative 16. So now let's go see if we can write our tangent line. So y minus 91 equals negative 16 times x minus 0. And it's okay if you use x's and y's instead of t's and h's because you're getting a tangent line. You're not doing the whole function thing. So this one's easy to simplify. I'm going to go ahead and do that. So there's my equation of my tangent line. And then it wants me to approximate the internal temperature after 3 minutes. So after you've let it cool for 3 minutes, what's the temperature? So that is approximately this negative 16 times 3 plus 91. And you can leave it like that, but you can simplify it, since it's just our notes, to 43 degrees Celsius. So that cooled a ton over 3 minutes. That room temperature brought it down. Okay. Last one. See if you can. Oh, they don't even want you to. Look, they took the implicit derivative for you. How nice are they? You're like, no, they're not. They're not nice. They make me do hard stuff. Okay, so they already did that whole implicit derivative and they want the equation of the tangent line. Okay, I've already got a point. All I need is a slope. Sweet. So we're going to evaluate this at that point to get my slope. So that would be 1 over 3 times 1 squared minus negative 1, 1/4. So now I do y minus y1 equals my slope, x minus x1. Sweet. Okay, A was pretty nice. Boom. So now we want B. B says find all the coordinates of all the points. That's the little thing. It's not just x values, which a lot of times it says, but this one wants points to which the line tangent to the curve is vertical. So here, if I kind of think of a vertical tangent, those would be like the vertical tangents of like a circle or something. And I know that when I have a vertical tangent, I have a slope of not 0, but undefined. Sorry. So when do I have an undefined slope? When I have a number that's not 0 over 0. That's going to give me this vertical tangent line. So I look at this slope, and it says, I want to know where this guy is equal to 0, but this is not 0. That's where a vertical tangent line would occur. So I know that that's where x equals 3y squared. So now I have to use this information that they gave me, the y cubed minus xy equals, what was it, 2? And everywhere I see an x, I'm going to go plug in 3y squared. So that gives me negative 2y cubed equals 2. Y cubed equals negative 1. Take the cube root, and I get y equals negative 1. Okay, so I know what y is, but it wants a point, and so far we have the y value. So to find the x value, I can come back up here and plug it in, squared, and get 3. And there is the point of wherever that graph is at 3, negative 1. Maybe it looks like this or something, that you're going to have a vertical tangent. All right, see you guys soon.